Now, before we do a question and I show you a nice meme to wrap up the lesson, I'd like to cover one more way in which you can think about the direction of the force and how it arises. So again, we have the same scenario, the wire. Around it, we have a circular magnetic field, like so, which we can find using our right hand corkscrew rule. And again, we have these magnets over here, north and south. Now, this is a 3D image, right? So the magnets are actually going to be blocks, something like this. Say that you are looking at this whole system from here, okay? Your eye is placed here, you're viewing it from the sort of butt of the wire. And so now if I redraw this scenario, we can see that the field lines will be circular again, something like that. And I've represented the wire with a dot because we're looking at it from the side. So yeah, in this case, the magnetic field due to the wire is something like that. And due to the magnets, we know it's something like this. And so what you see is in this region over here, that is in front of the wire, if we're looking at it from here, in this region the magnetic field lines are in the same direction due to both sources, so they're going to add and we're going to have a stronger field over here, or we're going to have more magnetic flux density over here. However, in this region the direction is opposite of the two fields, and so they're going to cancel out and we're going to have a weaker field or lower magnetic flux density. Now, this sort of disbalance, whenever it exists in nature, I mean, we physicists or aspiring physicists and nature agree on the fact that we don't like it. The universe tends towards entropy or randomness, disorder. In this case, we have a lot of disparity on both sides. And so we want to increase the entropy of the system and we want to make it more random. So the more dense field lines over here are going to want to spread out and help out the region here, which is less dense. And therefore you can sort of visually see that the wire is going to be pushed leftwards, or if we take this viewpoint again, it's going to be going backwards as we predicted. So you can think of it as the force is always going to be from a region of higher magnetic field density or magnetic flux density to lower, because the more dense side is trying to spread out its density as the universe tends towards entropy, which is, I believe, the first law of thermodynamics. Okay, let's solve a question. So I'll just zoom out. Yeah, before we solve it, I just want to mention one thing, that Fleming's right hand rule is often confused by people for the left hand rule. Remember that the right hand rule is only for when you're determining the direction of an induced current, and even then I personally prefer the left hand rule, but I'll explain the sort of technicalities in another video. Whenever we're determining the force, always use the left hand rule. Okay, so part 1. Label the direction of the current, magnetic field and force on the part of the coil labeled CD. CD. Okay. So the current is going to flow from positive to negative. So if I trace that, it's going to flow like that through CD. And it's going to sort of flow into the page. Okay, now the magnetic field, it's going to be from north to south. So like that. All right, and finally the force. So using the left hand rule, I'll align my index finger with the field, this with the current. Okay, so CD is going to be pushed downwards, a bit of an awkward position to hold your left hand in. And now we have to repeat the same for AB, part 2. So in AB, the current is going to flow like this, so it can return back to the negative terminal of the battery. And again, the magnetic field lines will of course be in the same direction, like that. So repeating the left hand rule, we get the force is going to be acting upwards over here. Now it's asking us to explain the origin of this force in terms of the charge carriers in a wire. So in a wire, we know ultimately that electrons are flowing, although in the opposite direction to the conventional current. Now, even though we label current like this, actually what's doing the work, what's creating this magnetic effect is the movement of the electrons. If you remember from Faraday's law, and whenever you've studied magnetic fields, we'll only have a magnetic force when we have the movement of two charges relative to each other. So it always comes from the movement. And so in this case, the electrons are moving due to the current in this opposite direction. And so we can calculate using the left hand rule the force on the electrons, and we'll see that ultimately this force on the electrons is in the same direction as the force on the wire. So the force on the wire is because of the force on these electrons, and since the electrons are contained within the whole wire feels a net force downwards. Okay, now they've given us that BC is 1 meter, alright, and the current in the ammeter is 2 amps. Okay. Find the magnetic field strength if the torque of the motor is 10 newtons per meter. Alright, so here we're going to have to use a bit of our knowledge from forces and energy and motion. So first, just observe the fact that since the force on AB is upwards and CD is downwards, this whole coil is going to rotate like this, which is how motors work, which is how motors actually turn. When we apply a current, they'll rotate because of their because they have these coils of wire inside a magnetic field. And in this case, we're just looking at one coil, but in reality, there are many more to increase the torque. Alright, so now if BC is going to be 1 meter, we know that to this midpoint, to the axis about which this whole coil is revolving, let's call that point O. So BO is going to be 50 centimeters or 0.5 meters, and the same for OC. So this 10 Newton per meter torque is going to be equal to the torque of this arm, which is let's say F, the force that is being exerted, into the distance of it from the pivot, so into 0.5, plus for this arm again we have F into the distance of CD from the from the axis, which is 0.5 meters, which is equal to just F, the force. Also, sorry, this should be Newton meters and Newton meters over here, because torque is going to be force into distance, so Newton into meters. Now I've taken the magnitude of both of these forces as the same because from our equation, our favorite equation, Bill sine theta, for both of these arms, although the direction of the forces is opposite, the magnetic field strength, the current, the length and the angle they make with the magnetic field, 90 degrees, is all the same. And so the magnitude of these forces will be the same. Interestingly, if you see the sections BC over here and say AD over here of the loop, when the loop is flat and is perfectly parallel to the field lines, then the current, or sorry, the force in BC and AD will actually be 0 because they're parallel to the field lines. So the angle theta they're making is equal to 0. And if you remember, sine theta is going to be 0. So this whole product will become 0, and hence the force due to the magnetic field in these two sections will be 0 at this moment in time. Alright, coming back to the question, so we have to find the magnetic field strength. So F is equal to Bill sine theta. If we rearrange that to give B the magnetic field strength, we get. Now we can substitute the value of force that we got from here, 10 newtons. This is in Newton meters, although we accounted for that when we multiplied by meters. So the force is going to be 10 newtons, and we'll divide that by the current, which is given as 2 amps, times the total length of the coil. Oh, I think I forgot to mention that, sorry. So we're assuming it's a square coil, and hence if BC is 1 meter, then DC will also be 1 meter, and BA, I'm so sorry for this cluttered drawing, but BA will also be 1 meter. And so if we take the total length, because we found the total force here on both sides, because we were given the total torque. So therefore, if we take the total length, it's going to be 1 meter plus 1 meter, 2 meters. And sine theta, our theta is going to be 90. So it's going to be sine 90 degrees, which is equal to 1. And therefore, we get 10 upon 4, which is equal to 2.5 Tesla. That's a very powerful field. And so you can see how in electric cars we have not only high current running through the wires, but we also have a very, very strong field needed between the magnets so that we can produce enough torque to actually make the cars move. And although the values here are slightly different, we won't have like 1 meter long coils inside probably, and we'll have a lot of coils, but you can get an idea for just how strong these motors and their magnetic fields need to be. Alright, and with that, I think we're done with this lesson. Thank you so much for watching. If you have any questions, please let me know down below. And I'd really recommend you check out the links in the description, especially the one about special relativity and how length contraction plays a huge part in how magnetism arises. It's really interesting. And alright, until next time, thank you so much for watching, and bye-bye.